שמח לארח את דן וילנצ'יק. So, Dan Vilenchik.
English.
Dan Vilenchik holds a PhD in computer science from Tel Aviv University. He did a postdoc at UC Berkeley and UCLA. He is currently a member of the School of Electrical Engineering at Ben-Gurion University. His research includes both theoretical, like challenges of high-dimensional data, and applicative, mainly NLP aspects of machine learning. And today, he will take us from theory to practice and back, and talk about stance detection as a case study. So, Dan, the stage is yours.
Okay, so thank you for the invitation. So it's actually the second time I give a talk in this forum. Last time was in Zoom on a different problem, so it's always better to be in person. So today I'm going to talk about a work. So I know this learning club is more geared towards theory. So I think this talk could be interesting to see how theoretical results, mainly that came from in my PhD work, inspired an algorithm that actually gave really good results in a practical problem, stance detection, that's involved in natural language processing, and some insights that I think can go back to theory. And I think this interplay between practice and theory, this case study for me was really interesting. Feel free to stop me. I don't assume any knowledge in NLP or in the theoretical background. So the theoretical roots of this work come from random graph theory. So this was in my PhD. I studied random graphs, and especially I focused on NP-hard problems like coloring and satisfiability, and that in the worst case are NP-hard, but if you assume some distribution and some generative model, then you can ask, are there algorithms, heuristics that can solve with high probability or with high probability such random instances? What approaches work? In what range of parameters? So I'm sure you're familiar with this type of research. There's a hard problem. You assume some generative model, and then you approach the problem with theoretical tools. You get some insights and publish nice papers. We focused on what's called planted solution distributions. So those are distributions where you force the random instance to have a certain solution. It doesn't tell, like you take a satisfiability problem and you force some assignment to be a satisfying assignment. You don't tell the algorithm which assignment you planted, but then you ask the algorithm to recover some satisfying assignment. So we focused on what's called planted solution distributions, which are random instances of satisfiability or k-colorability, where you force the graph or the instance to have a solution. So you know you have a promise that the graph is, let's say, 3-colorable. Now you need to recover some 3 coloring. Still, the problem is not, it doesn't make the problem trivial. Well, these planted solution models were, sometimes we got, they were, let's say, people said, well, it's easy, you plant a solution, it's not interesting. But as we will see in a second, I think they gave a good intuition to the problem that I'm going to discuss today, and all the theoretical tools that people developed, including in my research, to study those distributions. And we will see how this planted distribution arise naturally in various machine learning problems. Okay, so the problem that I'm going to discuss today is called stance detection. So there are forums where people, there's a topic, for example, do you support gun controls? And then in those forums, people can debate. If you are for, if you can raise your opinion and write if you are for this or against. And the classification task is given such a forum to understand or to classify the users into the two classes, pro and con. Okay, so that's the problem. You can use the text, you can use the graph, you can use whatever you want, but the goal is to get the highest accuracy possible, as always. And this problem of stance detection is later used for other NLP tasks, such as discourse parsing, detection of fake news, and so on. So here is an example of one such platform. It's called Create Debate. So the topic is, do you support, do you oppose abortion? And then there are posts. So people can respond directly to this post or reply to another post. So naturally you get a tree. There is the OP, that's the original poster. And then each node is a post. It's not an author, it's a post. So an author can post several posts, and the color are pro or con. So let's see an example. So that was the original claim. 40 million people have died because they were aborted. How many Einsteins or Edisons did we kill? And then A, which opposes this opinion, says that this point in view is moot because it could have just as easily been the next Hitler. And then E, which agrees, says make that 240 million. D, which opposes, replies somewhere down the tree. You don't have to tell me that. I agree with you. So he opposes, but he uses the term I agree with you. So this already gives you some notion that just using text or rules could be misleading. And then, And then H that agrees with D, but so D disagrees and uses I totally agree, and H agrees with D and also uses I totally agree with you. So just using language to understand if people are for or against a certain position is too naive, or it's too naive to use it as rule-based. Yeah, so the challenge is to decide the stance, but using text in a simple way is misleading. Of course, you can use a word embedding or advanced tools in NLP. We will compare to them. But in this work, we took a completely structural approach. And the working hypothesis is that if A replies to B, then they tend to hold opposite opinions, opposite stances. I mean, it doesn't have to be like that. That was our working hypothesis. Again, we'll see in a second how it's all connected to those nice graphs that I told you about. And this was, I mean, it's a logical assumption. It was observed before in the literature. And we came up with an algorithm which is completely based on the structure of the conversation, which detects the stance. And all the inspiration or the machinery for the algorithm comes from the theoretical work that I described, and I'll also say here. Okay, so since we are working on a graph, the first step is to turn this tree, the conversation tree, into an interaction network. So in the interaction network, the nodes are the authors, and you can place an edge between two. We place an edge between two authors if they replied to each other. Now the edges are weighted, and you can weight them according to various parameters of the platform. For example, the number of times that they replied to each other. In some platforms, you can reply. You can also quote. So there are different ways that people reply to each other. So the weights could take that into account. But at the end of the day, you get a graph which reflects the conversation. And then if we believe the assumption that if A replies to B, then they tend to hold opposite stances, then the logical thing is to solve a max-cut problem. So you would expect that the max-cut would correspond in some way to the stance. So that's the first intuition. However, max-cut is an NP-hard problem, so you cannot just solve it directly. Even if the graphs have a few hundreds of nodes and many edges, or it could be thousands of nodes, we'll see the discussions, but you cannot solve max-cut directly. You can use a greedy approach. So for every vertex, so here it's just the BFS, you start with the vertex, let's say, with the highest degree, or with some vertex, and then you place the other vertices so that the maximal number of edges are cut. And then you just, for each vertex, you decide greedily on which side to place it. So for example, here, as I said, it's a BFS, and you can think about such a partition of pro and con. In this case, the graph is bipartite. And we noticed, and we'll see later on, that this heuristic works well. If the graphs are simple, if the conversation is roughly like a tree, then this gives you already quite good results without even looking at the text. But in general, the greedy only guarantees half approximation for graphs. And indeed, if the network is more complicated, so you have a dense subgraph, then the greedy makes many mistakes on this dense subgraph, and then these mistakes are propagated to the simple components that are connected to this graph. Okay, so you can think of the graph, indeed random graphs with a constant degree are composed of a dense core and then many simple tree or maybe tree plus cycle components that hang on this core. And the greedy doesn't work well on the core, and then mistakes propagate. Yes?
We said there's an edge in the graph if it's one post is a reply to another, or if it quotes another post?
Yeah, so first the graph is undirected.
Okay.
In this work, I mean, maybe directions help more. So if A replies to B or B replies to A, we put an edge between them. Now, depending on the forum, you have a reply button, you have a quote and reply. So there are many ways that people interact.
Yeah, if it was just reply, it would be a tree, no?
No, because A replies to B, B to C, C to A. There are cycles.
The node is the person, not the
Yeah.
person.
So then, so that was the slide. The conversation is always a tree, right? Because D appears several times per post. It's always a tree, but we turn it into an interaction graph of users. We want to classify the users and not the posts. Yes?
So the assumption is that more there are interactions or replies or quotations, it's more likely that it's like the opposing views. Right?
That's the hypothesis, working hypothesis. Mm-hmm. It could not be. It could be false, and then we would get, and then max-cut wouldn't give you the right results. Okay, so a constructive way, again, it comes from random graph theory, is to think of the graph as some core, a dense subgraph, where it's complicated for the greedy, but on the other hand, because it's dense, there would be some signal to pick from it. And then once you nail it down, you can propagate the labels, let's say, safely to the easy components. And this is also part of the algorithm. I'll wrap everything together in a complete picture. But the greedy is too naive for this complicated graph. And then how to proceed. So I don't know if you did some approximation algorithm course here, but the way, the state of the art to solve max-cut is by using semi-definite programming. And this is what we used. But then, as we noticed later, this embedding gives more than the max-cut. And that was the part of back to theory, which I'll cover. But So the solution is we came up with a new type of speaker embedding, which is based on semi-definite programming. We embed the speakers in the core, and then we propagate the labels. Okay, so before I present this semi-definite programming-based embedding, so in general, people use embedding in machine learning, mainly in language tasks, but more generally. So embeddings are mappings from nodes. It could be words, in our case, speakers, objects. They are embedding from high-dimensional objects to low-dimensional objects. So you can think of a one-hot encoding. That's a high-dimensional naive or let's say, naive representation into some low-dimensional space. So n nodes are embedded in a d-dimensional space, and typically d would be much smaller than n. The dimension could or could not be a parameter, as we'll see here in SDP. The dimension is fixed. You cannot. It's not like in neural networks where you can control the dimension of the embedding, and embeddings have a useful property. This is why people embed. Typically, it's a cosine similarity that implies some semantic similarity. So objects that have vectors that are close to each other in cosine similarity tend to have similar meaning, like words or stance in our case. But what we understood here, that the embedding gives more information than just the binary max cut. Okay, so typically when you think of an approximation algorithm, then you say, okay, I have a binary problem. It's NP-hard. I relax the constraints to vectors, or in linear programming to real numbers, and then I round the solution. But as we will see here, the embedding itself, like in word embedding, gives more information than just the max cut partition. And the embedding should be computed efficiently. Otherwise, again, it's not interesting. And the embedding is derived against some optimization problem. So most famous embedding, it's small, are words embedding, like word2vec or BERT. So people train a neural network using in a supervised or in word2vec in an unsupervised manner against some optimization function. And then at the end, you get embedding. So here you see, okay, so I'll skip to this bigger picture, a larger font. So, and then, for example, the famous examples of those word embeddings. For example, the difference between king and queen is like man and woman. So you get you catch with those vectors like semantic meanings like gender or tenses or capital to state. Right? So you start with the text, you train a neural network, and at the end you get this magic that those vectors you can derive information from. Our embedding is different, so we use semi-definite programming. In semi-definite programming, each vertex is embedded into a unit vector on the unit sphere. And the optimization problem is a semi-definite program. I'll present in a second the relevant SDP. The SDP that we used is the max cut SDP proposed by Gomez and Williamson in '94 to solve the coloring problem or the K-cut problem. So max cut is the binary case, but in general they used it for K colorability. And this is the semi-definite program. So we can quickly go over it. So U and V are vectors. So if you think for a second on the max cut problem, so if U and V are just, you restrict them to be plus minus 1, not vectors, then you want to maximize the sum over all edges. So ignore the weights for a minute. Think of it as weight 1. And so if U and V if U and V are on the other sides of the cut, so plus and minus 1, so their product is minus 1, and this entire thing contributes 1. And if U and V are on the same side of the partition, then either it's 1 times 1 or minus 1 times minus 1, and then this contributes 0. So this is just the same as saying I want to find a partition of the vertices plus or minus 1, assignment of plus minus 1, either side of the cut, that maximizes the number of edges that cross the cut. As we said, this is NP-hard, and therefore the SDP relaxation relaxes the plus minus 1 integer variables into unit vectors. And you solve the problem. You get some embedding. So for example, if you look at the bipartite graph, then the only possible embedding is the following. I'll prove it in a slide in the next slide. It's a really simple proof. But that's the only possible embedding. Assume that the graph is connected to antipodal vectors. Okay, so one side of the cut gets, let's say, the green. All those vertices on one side get the green vector. All the vertices on the other side get the red vector. The dot product is minus 1 of antipodal unit vectors. And then you just get the number of edges. Right? So in the bipartite case, max cut solves it exactly, SDP, and it's not a surprise because to find the max cut in a bipartite graph, it's easy. It's two coloring. It's in P. So it's no surprise that the SDP gives you this very nice solution where you can read the bipartition immediately. Yes, question?
This relaxation is not the same as relaxing to have each one not be pro or con, but a continuous number between 0 and 1, right? It's not the same kind of relaxation, or it is equivalent.
So pro and con is from the NLP domain. So here, this relaxation just tells you that the vectors can be any vector on the unit sphere. Instead of plus minus 1, you want to maximize over vectors of the unit sphere. In this specific case of a bipartite graph, the solution of the SDP has to be of this specific form. But in general, the vectors are in Rn, and the solution could be any configuration of vectors that optimize the SDP. Okay? So it's not necessarily this very nice solution. We will see why, under what assumptions we can get this solution and when it's useful. But like in word embedding, who says that you will get a useful solution that synonyms get close vectors? Nobody, but it happened. Right? So also here we'll see, but here it's rooted in theory, when do we expect to have these very nice solutions? But in general, the vectors are in Rn, and you cannot restrict the dimension. If you could restrict the dimension to 1 or 2, then the problem is again NP-hard, solving this, because it's again a non-convex problem. Okay, so back to our stance detection problem. So what we would want to have happened, is that when we solve the SDP on the interaction graph, then we get maybe not the same vector for all the ones that are pro, but get a cone which is distinct from the cone from the ones that are con. So we get two cones, which we can then separate, let's say, using a random hyperplane, or there are standard techniques where you can round the vectors back to an integral solution. That would be the useful embedding property. If you think of a useful embedding property for words, synonyms, or capitals, whatever semantic relation, that would be the useful property here. And the question is why and when would this useful property manifest? When would we have this nearly integral solution in a general graph which is not bipartite, could be k-partite. So in general, those graphs are not bipartite. When would we have this solution? So here we take a small detour in theory, right? So everybody understands we don't expect this to be the solution in general. For a general non-bipartite graph, this need not be the case. Could be any configuration of vectors, and then, okay, you solve it, the embedding is meaningless. You cannot read anything from it. Okay, so you can think or model a discussion using the Erdos-Renyi random graph model, where you have, so think of, you partition the vertices into half, let's say half here and half here, and then you place an edge with some probability between two opposing speakers, and an edge independently with some probability, say the same probability, but smaller within the group. Okay, so you have this random graph. This is also connected to the problem of community detection, if you've heard of it. Right? So you have these random graphs where edges are more likely to cross the partition than to be inside the partition. And what do we know about such random graphs? So as we said, if Q is 0, so if the graph is completely bipartite, then you solve to coloring, it's in P, and then the embedding is one-dimensional. So let's see the very simple proof for that. So for every graph, the value of the SDP is at most the number of edges, right? Because here the contribution is at most 1. The dot product of two unit vectors is at least -1. So here you get at most 1. So it's at most the number of edges, and it's at least the value of the max cut, because it's a relaxation. You can always get the value of the max cut just by giving vectors to the right partition. But the SDP can give you a value which is larger than the max cut in general, and at most the number of edges. However, if the graph is k-partite, k equals 2, or for any k-partite graph, the max cut is exactly the number of edges. So the value of the SDP for k-partite graphs is just all the edges. Now, in the bipartite graph, the way to get an SDP value of exactly the number of edges is, so you assign here a vector. Now, all the neighbors have to get an antipodal vector, and then all their neighbors back here also get the antipodal vector, but the antipodal of the antipodal is the original vector. So in k equals 2, you get this, you get just from this simple geometric property, you get that this is the only way to embed, to solve this problem and get all the edges cut. Right? So you just have this unique solution for the k equals 2. Yeah?
So just to be clear, WV is just weights of the edges, right? Or
Yeah, so it works also in the weighted graph, but think of the weights as 1 in this case. But that's the only way to get here. So if you think of it, only way to get all the edges is just assigning the two antipodal vectors. In general, what happens if the graph is k-partite, or as I said, or two parts but not bipartite? So in the general, it's not opposite opinions, just different opinions or different stances. So it's not necessarily pro and con. You can have different stances. Again, the value of the SDP is the number of edges, but in this case, the simple argument of the antipodal is not true, because this is not the solution here. We'll see in a second what's the integral solution, but it makes sense because the problem is NP complete. You cannot expect such a solution. As I said, there is a 0.87 approximation for max cut, but it's a guarantee on the value. It doesn't say anything about how the vectors look. Are there 2 or 3 cones? It just says something about the value. And it's a first moment calculation. It doesn't say anything about with high probability. So this is the SDP program for a general k. Right? So if you plug in k equals 2, you get half. And this is just 1, which means that they are unit vectors. So, but in general, you get this. This is the solution. This is the formulation, and the solution, one solution, integral solution for the max cut problem on k-partite graph is the following. You look at the k-regular simplex, and you take the vectors that connect the center of mass to each of the vertices. So in the three-partite case, when k equals 3, you look at the equilateral triangle, and then you take those three vectors. The angle is 120 between each two. The cosine is -half. And this is one solution. These solutions, if you plug in, if you take these three vectors, you assign them to each part of the cut, then you get the number of edges. This is one possible solution to the SDP, which gives you all the edges. Right? You can verify it quite easily, and this holds for every k. Just the k-regular simplex increases in dimension. So here the dimension is k minus 1. Okay, so it's two-dimensional, the solution. This is one possible solution. But again, unlike the bipartite case, there is no guarantee that the SDP will give you this solution. If it gave you this solution, you can read the k partition immediately, or the k coloring. But again, this could happen for certain graphs, but there's no guarantee in general that this is the case. You can add a rank restriction. You can say, I want just the optimal solution over all solutions of rank 2. But then this constraint makes the problem non-convex, and you cannot solve it. But together with Michael Krivilevich, my PhD advisor, we proved that indeed for random k-partite graphs, or random k-colorable graphs, with a constant degree, you get this solution. So with high probability, if you run semi-definite programming, the max cut SDP on such graphs, you get this solution. And ideas from also came in previous work for other types of graph. I'll give you a hint of how the proof goes. I think it's again, it comes from theory of random graphs and spectral analysis, and it's a neat proof. I'll just hint the ideas in a slide. So you take the graph, your graph, and you add an edge, one edge between, just for the analysis, for the sake of the analysis, you add an edge between two vertices in the same class. Okay? And what you want to prove is that the value of the SDP, we know that it's at least the number of edges. And what you want to prove is that, and we know that the value of the SDP on the graph is at least the value of the SDP on the graph with this extra edge, because maybe you can gain something in the cut from this edge. Maybe not cut the edge entirely, it's continuous, but maybe you can gain something. But what you can prove is that for random graphs, you cannot. So the value of the SDP of the graph G plus this additional edge is still at most the number of edges. So you cannot gain anything from this edge. Now, the only way that this new edge can contribute 0 is that if XU and XV get the same vector. This has to be 0, right? You gain nothing. So the embedding of U and V is 0. They get the same vector. Now, this argument you can repeat for every pair of vertices in the same partition, and then you get that the embedding is exactly two-dimensional with high probability. The way you prove this inequality, that you cannot gain anything, so in optimization, it's very common to switch to the dual. You look at the dual of the max cut problem. That's the dual. And you just come up with a solution to the dual that has this value. Right? So the dual is a minimization problem. The primal is a maximization problem. And you use properties of the random graph to come up with a solution that has this value. I think it's a neat proof. And this is for random graphs. Right? So for random graphs, you get, if the degree is sufficiently large, so if there is enough signal, then you get this two-dimensional solution from which you can read the partition. And now back to stance detection. This is how the SDP, the vectors of the SDP look on the speaker graph. Right? So we ran this SDP with k equal 2 on the speaker graph. It's not bipartite. You can
SDP sometimes can take be very expensive, even though it's polynomial. What are
Yeah.
the nodes? How many nodes? How many
in the hundreds.
How long does it take?
So, well, the student did it, but it wasn't something that he called and say it doesn't. Plus, so they solve it, but perhaps not to the optimum. So I think the modern solvers are, they don't solve it like in the classical, let's say, ellipsoid or method. So this is the solution that we got on the speaker graph. So you see two cones. Right, so you see that here the embedding is useful. You see, I mean, some vectors lie out of the core of the cone, but the majority of vectors are indeed spread in two cones. Now, this is a PCA projection. There are unit vectors, so but you see that the length is almost 1. So there is almost no perpendicular component in those vectors. So this is a two-dimensional picture. The vectors are in Rn. So if we had, let's say, 300 speakers, so here the vectors are 300 dimensionals. But this is the picture that you would see in 300 dimensions, roughly. Right? You see it's almost 1, the length of the vectors. So that was, I mean, we didn't know. The theory said that if the assumption was true, that indeed max cut is the intuition, and what happened, and the knowledge from random graphs, then we would expect to see a two-dimensional solution. And indeed it happened, which was, I think, nice. So here's the algorithm, the algorithm for stance detection. So first we construct the interaction network. Then we compute the two cores. So we ran the SDP not on the entire graph. So we ran it just on the two core. That's a dense subgraph. Then we computed the SDP embedding on the two core. We rounded the embedding using random hyperplane. And then we got the initial partition, pro and con. And then we propagate the labels greedily in the simple components. Now, this algorithm of solving the core and then propagating, again, is rooted in theory. It's early works by Noga alone, already from 97. Again, partitioning the graph in this way, coming from the fact that for the dense part, you would know the coloring for sure, or with high probability, and then propagate it to easy parts. Okay, so we evaluated our algorithm on 3 forums, 3 debate forums. 4 forums: Create, Debate, and Convince Me. So if you want a break from your work, you can go to one of those forums and try to convince somebody. Good luck with that. So here you see the overall number of conversations. How many conversations contained a large core? So for example, in 4 forums, you can see that all the conversations were dense, so they had a large core. The overall number of authors was this, and most of them belonged to the core. In the other two platforms, most conversations here, especially, they were more tree-like, so they didn't contain a large core, and also most of the speakers did not belong to the core. So we would expect that the greedy algorithm here would be just as well as the SDP, and we would expect here that the SDP would give an advantage over the greedy. And this is what we saw. Now, these are, let's say, state-of-the-art algorithms for stance detection. Especially interesting is this last algorithm. So, okay, I'll say that some works work on the post level, so you can ask whether a post is pro or con, or the author in general. You can use local information or global information. You can use text or structure or both. And you can be domain-specific or not. But if you look at this last work, so this last work uses both text and structure. It uses neural networks, and it computes an embedding that takes into account both language and structure. Right? So that's the most advanced embeddings when you solve practical problems, they embed language and metadata together. Other works use just the language. And here is the results that we got. So what you see here is an average over many discussions that belong to the different topics. So we had, again, we used the data that previous work used. So there are here I present 4 topics, that there were many discussions around those topics. It's not a single discussion. In all discussions, the baseline is roughly 50-50. Okay, so roughly 50 people are pro and con, so it's a balanced classification problem. Create debate is was a very sparse, gave a tree-like speaker graph, and we see here that the greedy approach, it was in many cases, okay, either like or better than the very sophisticated neural network embedding. And the SDP, STEM is the SDP-based algorithm. It was roughly like the greedy, slightly better, not dramatically better. Again, as was said here, SDP is computationally expensive. Even though it's polynomial, it requires a lot of computation, and greedy is, you can implement it in linear time. For forums was a very dense platform, so people tend to interact much more with each other. And here we see a large gap between the simple greedy and the SDP-based. Here we can see the power of this more intensive problem, and again, an improvement. So this gave the state of the art of existing world without looking at the language at all. So it's just the structure, no language. Okay, so back to the question. So we got an embedding, right? So we have those cones. And the question is, I mean, in the algorithm, we just round the embedding. So you can say, okay, so you just solve max cut. But as we will see here in the next few slides, the embedding gives more than just the max cut. So we looked at the embedding. Yeah.
About the previous slides, when you try the greedy approach, it's on the, because you start from a tree structure and convert it in some sense to a dense graph. You can run the greedy approach on the tree structure as well, right? And then, I don't know, average over author or something.
Yeah, we ran it on the speaker graph. Yeah, you can run it also on the tree. Perhaps the student tried it, but yeah, I mean, it's basically the same, just that the weights are different, right? So you get more information in the speaker graph if you want to partition the speakers, in the sense of the max cut. But yeah, it's true. You can run it on both. The SDP you can only run on the speaker graph.
Yeah, I understand, but the greedy approach, it works better for trees. You can run it on the just original.
Yeah, it doesn't mean that the partition would be correct.
Right.
If it's very, I mean. Okay, so in this table here, you see what happens when we narrow the diameter of the cone. So if we take, you see the direction here, in black, it's just the average over all of the two cones. So we know the ground truth, right? So we can play with it. So what we see here, we compute the accuracy as we take smaller and smaller cones, tighter and tighter cones, and we see that as the cones get tighter, we see that the accuracy improves. So indeed, the embedding has more meaning than just the max cut. It means that that users whose vector is closer to the average, this would also be the PCA direction, right? The direction with largest variance. So the closer your vector to this good direction, then the more confident the algorithm is. So we could also derive confidence level in the result from those embeddings. So that was one thing that was that was also, I'm not sure surprising, but was also a nice side effect. Okay, so to conclude I think this theory plus practice picture, so what we saw here is that if you have controversial topics, right, and we'll see it in a slide or two. So if you have controversial topics, they lead to heated discussion where people interact in a meaningful way. Now, these heated discussions generate a graph that is dense. Okay, and it's dense, but it has this additional max cut property, and both of them force the SDP to have a low dimensional embedding and a meaningful embedding. This is what we saw. This was the property that we used. So to verify or to see how correct this picture is, we also computed the average valence of the discussion. So valence is defined, it's not the sentiment. So sentiment is it a good or bad? So is it positive or a positive sentiment or negative sentiment? The valence is the magnitude of the sentiment. Is it a strong sentiment or not? So we used off-the-shelf senti-strengths. So there's a package a library in Python where you can compute the strength of the sentiment, and we saw a correlation between the sentiment of the discussion and the accuracy. So the more heated the discussion was, the more accurate the solution of the SDP. The tighter the cones, the better the rounding. So it all came together. So here is a work that continues the work that I said. So the previous work, I forgot to give credit. So I'll switch to the first slide at the end. So it was published in the recent AAAI. It's a work with Oren Zur, who's also a researcher at Ben-Gurion University. He works in NLP and 2 students. So here we see how so another discussion, would school uniforms improve our schools? Here you see the full interaction network, how it looks, and then the core. So out of 159 speakers, most of them belong to the core. So all of these simple or one degree vertices are removed, but it's peeling. It's a peeling process, right? Once you remove this becomes 1 degree, and then you remove it also. So it's an iterative peeling process, but it stops very fast. You end up with a dense graph very fast. In some platforms, this peeling process just finishes the graph. There's no to-core. And here we see, so in this work, we are trying to understand the connection between the actual content to this structure. So here we see 2 cones, but they are much more widespread. Again, the picture is almost 2-dimensional, right? So you see this is the leading principal component. So the vectors are almost unit vectors on this PC, right? So you see this. You see these directions that splits the vectors. The cones are wider here. But what we try to see if there's a connection between the content and how close it is. So here is one person that's against uniform schools, 159. So he says schools uniforms decrease bullying. He's for this. School uniforms decrease bullying, violence, and grades have actually been, I'll read from here, actually have shown to increase when uniforms are implemented. Perhaps once you take away the style of dress, you may actually have to get to know the child underneath. So that's a good argument. On the other side, you see 216, also very close to the PC directions. That's the first here. Uniform, there is no point of wearing a uniform. It takes away your individuality. It's a waste of money. And then, so we see two good opinions in both ways. And then there is 204, which is perpendicular to this. And it's schoolboy, Chuck Norris's vented water. Just what type of vent was it? Something that's not related to anything. So one option, one thing that we are checking is perhaps you can use this structural embedding to summarize the discussion. So summarization is another very important NLP task. So you have a discussion and you want to know what was going on, or give me the best opinions pro and con. So this is something that, again, we're checking the connection between structure and language. Okay, so to conclude, I think that so one level of abstraction upwards. So what we've seen here that we have an event that has zero probability and it happens. And this leaves a structural footprint that you can discover. So in random graphs, if you take just a random graph with average degree but sufficiently large, then it won't be k-colorable with high probability. So there's the k-colorability threshold, and it's a sharp threshold. And once you cross it, the graph won't be k-colorable. But you can condition on it being k-colorable, and then look at what happens. Now, this conditioning on an event that has zero probability leaves this amazing footprint that the SDP suddenly becomes two-dimensional. In our case, the conversation is governed by one rule, so there are many possible rules. It doesn't have to be that people react to each other if they disagree, but this happened to be the rule that was chosen out of many possible rules. Again, you have this structure that emerges when you condition on this really rare event. So you have a random structure, complete chaos, conditioned on some planted event, and then you get structure. Again, language, right? So there are rules, context, but you have gibberish, right? It's a random mixture of words. Once you condition on certain context, you get a structure that word embedding discover. So I think this randomness with structure is interesting to see this connection. And the footprint, both in word embedding, in our case, was low dimensional. So it's, in some sense, you can think of it as Occam's razor. So the simplest possible explanation is the correct explanation. And in this case, simplicity is the dimension of the embedding. And it can be discovered in polynomial time, which is also non-trivial. Why would you be able to do it? But so it happened. And in both cases, also in max-cut and in word embedding, you can think of adjacency matrix. And so with the graph, you can associate an adjacency matrix, as you all know. And also with the text, you can associate an adjacency matrix, which words appear with each other. And in both cases, you have a low-dimensional factorization. So if you take your adjacency matrix and you decompose it as a sum of rank 1 matrices, you will have, like an SVD decomposition, you will have very few, so you will have one or two low-rank, one-dimensional matrices with very large eigenvalues that dominate the structure. So again, it's all connected. It all comes from the fact that you have this low-dimensional factorization. So back to theory. That's the last slide. So I think in computer science, SDP is always viewed as an approximation algorithm, as never as a tool by itself with self-interest. So it's just, okay, we cannot solve an integral problem. Let's use SDP, state of the art. But I think that at least as we have seen here, the vectors themselves give more information than just the cut itself. They give confidence. They can be related to other meta features like how concrete or how good the opinion is, the stance is. So I'm not sure if this is the right community, but I think that one thing that people study random graphs. But random graphs are with a fixed probability for an edge, like percolation schemes. But I think that what emerges from this work that degree distribution sequence, and that's another random graph model, but it's far less studied, where you fix a degree distribution and then you generate random edges, but according to the degree distribution. Perhaps it models better real-world problems in the sense that you can study the relationship between the vectors and the degrees. Because if you have the same average degree for all the vertices, then you lose something. So we saw that, for example, we proved that the solution of the SDP in such random graphs is two-dimensional. You don't get cones. You just get three vectors in the 3-part 8K, each pointing for the class, but maybe something more refined where you have different degrees, and then you can show that the smaller the degree or the larger the degree, the better the vector, the more confidence you have in your answer. And this goes back to problems like community detection, where, again, the assumption is the degree is Poisson, and then you lose something. So let's finish with limitations. This approach was good for offline analysis, those well-constructed debate platforms. We tried it, for example, on Twitter. We got worse results. And the fact is that in Twitter, people don't just reply if they oppose. They reply for many other reasons. So this assumption is not true. People spam. There are a lot of spammers, a lot of trolls. In those platforms, people go there to debate and not to spam. And so, indeed, this assumption was crucial. And when it was gone, then you just have this random graph, no structure, and the SDP crashed. Everything crashed. And as I said, in continuous work, in the following work, we try to understand what happens with vectors that are perpendicular. Is it a neutral stance, a third stance, or just irrelevant stance? So thank you.
Did you try spectral clustering for the same task?
Spectral graph theory?
Spectral clustering.
No, we didn't try. I think for random graphs, so that spectral clustering for random graphs is basically, so SDP is a generalization of spectral clustering for random graphs.
Just in terms of computation, spectral clustering will be much more efficient, and I wonder the special properties that you have in this problem, if it is not already captured by spectral clustering. So if you will apply spectral clustering, you may get the same result, but much more efficient in terms of computation.
So first, it's something worth checking. Spectral clustering doesn't give you an embedding. So it just gives you a cluster. Are you in?
No, it does. It's basically the same. You get vectors representation for every node in the graph. You just not solve the max relaxation problem, but a slightly different problem, and you just need to do SVD once.
Okay. For random graphs, my suspicion is that it's the same. It comes from the fact that the largest eigenvalue, but in negative sign, gives you the partition. SDP, I mean, the proof that I showed with SDP exactly relies on this intuition. Thanks. Things worth checking.
Is there a notion, in some sense this is a classification problem. There's no train and test, right? You only...
It's unsuper. I mean, we use this as an
unsupervised problem. It's not a classification problem. This is why I asked about spectral clustering, because this is a classical clustering.
In the end,
we view it as a clustering. The other ones, they train the model against the gold standard,
So
which
that's what
as
I
a
wanted
classification
to ask.
problem.
The neural net, how does it work?
With the label data.
So they're labeled as pro and against?
Yeah.
I see.
Also what we check, I mean, all those data sets, they come labeled. It's gold standard. Those convince me for forums, create debate. There are gold standards that people labeled manually with a lot of work during the years. And you can train a supervised learning classifier or embedding. Cross-validation, the same.
So I think you're selling yourself short.
Yeah, it's
not saying
unsupervised.
that you're not using supervision and they are.
Yeah,
that's very
I think,
interesting.
yeah. In the paper we make this point, but in the talk, yeah, it's another, that it's unsupervised. By the way, it was rejected from all language conferences because first they said, what's SDP embedding? I mean, how does it connect to neural networks? They couldn't understand that there are other ways of embedding. And it doesn't use language at the end of the day. So
You should just call it SDP, neural SDP, and then it will be.
like deep reinforcement learning, there is nothing deep, but if you add the word deep SDP, then it could have been the solution. SDP, like that.
Now you got it.
That's the next paper.
Any more questions? Okay, so thank you again, Danny.
Thank you.